Hey, I'm Stefan, the organizer and host of the emBO++, the next level conference for embedded software developers. The talk you're about to watch is about the cost of C++ smart pointers. It was given by Tamas Ruszkai at the emBO conference 2021, and thanks to Leica Geosystems, you can check out this talk for free.
Hello, good afternoon. Welcome, everybody. Actually, my presentation, my name is Tamas Ruszkai, and then my presentation is going to be about the smart pointer abstractions and how low or zero cost they are in C++. As I mentioned, my name is Tamas. Actually, I work for the Leica Geosystems in Switzerland. And then we work on the projects, what you can see here. These are some products from our product portfolio. And then we work in the embedded projects. So in the embedded projects, we have some microcontrollers, but mostly our projects work on a single board computer. So we are somewhere in between the microcontroller and the desktop applications. That's why the performance is important for us, but we are not so strongly restricted like you are restricted on a microcontroller. For example, heap allocation, threadings, and these nice features of C++ or the operating system is available for us. And then, as I mentioned, the cost in the embedded is very important. And then the C++ is famous for its low or zero cost abstractions. And then we use for the memory management quite often smart pointers. And then I was curious that how it compares using smart pointers to row pointers. The subject of this investigation was comparing the shared and the unique pointer versus the row normal asterisk pointer. The environment where I did this experiment was Visual Studio with optimized code. And then the method how I did the measurement, it was not using some profiler tool, but I was analyzing the C++ source code, and then I was also analyzing the assembler code that was generated out of the code. The first aspect of the investigation was analyzing the memory consumption. And then this is the good old C++ pointer with the asterisks. We know that we have one pointer that is pointing to some object that is most likely on the heap. The pointer can be on the stack or can be also the heap. But the size of the pointer, it is exactly the size of one address. So it depends on the platform, can be 64-bit, it can be 32-bit. The interesting thing here with the unique pointer, that the unique pointer is nothing else, just a very cheap wrapper around the pointer, because as we can see here, internally the unique pointer class contains just a pointer. So basically the size of a unique pointer, it is the same as a size of a row pointer. Of course, we have again the object here on the heap, but this is the same. And now let's have a look on the shared pointer. As we can see here, the memory layout of a shared pointer is more complex than the two others. And then we can see here that beside the normal pointer, we have also another pointer. So it means that in the shared pointer instance, this is a size of two pointers. One pointer is pointing to the object, and then the other pointer is pointing to some administration area. And then in this administration area, we see that there is a counter that I called here it's strong counter. So basically this is how many shared pointer is owning the integer object, and then we also have the weak pointer concept, and then for that one we have another counter. We have some other data. We don't investigate or we don't look into that, but just to give a feeling, so you will find here some custom deleters, custom allocators, such thing. The interesting design choice was for the shared pointer that they did not merge it. So would have been possible that the shared pointer contains only a pointer to the control block, and then inside the control block I have the pointer, so the normal row pointer that points finally to the object, and then it would be the same size as the unique pointer. But we will see later a bit what was likely the reason for this design choice. The next point of the investigation was the runtime aspect. So I try to put here different price tags on each of the steps, what is happening. These dollar signs here are not exact numbers, so it doesn't mean that if something is $1, then if you have $3, then it is 3 times more expensive. It is just more or less the order of the complexity or of the cost. So with the row pointer, first when we allocate something on the heap, then it is quite expensive. Allocation of the pointer is quite often free because maybe it is just part of your stack frame. So it is just moving the stack pointer, which is anyway done. And that's why I consider it just a free operation. And then you have to put the address of the allocated object into the pointer, and this is also a quite cheap operation. So that's why I just gave here one dollar sign. The interesting point was here that the unique pointer seems to be not any more expensive than the normal pointer, because the allocating the object on the heap is the same cost, of course, but the call to the constructor of the unique pointer is inlined, because the unique pointer, it is a template class, and then the compiler sees the full implementation of the constructor, so it has the chance to inline it, and the functionality is also quite simple. So in my case, and I guess also for the most of the compiler, it just simply gets inline, and basically it is the same effort like for the row pointer. So basically it is just this inline constructor just contains an initialization of the pointer. Basically we put the address of this object on the heap into the pointer. Shared pointer is a different beast. So we can see the price tag here is quite big. Of course, again, we will have to allocate first the object on the heap, then we call the constructor, but for the same reasons as for the unique pointer, this can be inline, and this is very likely to be inline, especially for the optimized code. Then we will have to initialize 2 pointers instead of 1 pointer, but this is also not a big deal, so that's why I also just put here $1 sign. But now here comes the big beast. As we have seen, when we create this control block, this is a different heap allocation. So it is separate from the object what the smart pointer points to. And then because of that, I put here $3 signs. We will see later how we can optimize for this step, because this is the most expensive step of the shared pointer, and there is a technique how we can reduce this cost. So now we know what it means to create a smart pointer. Now let's see that what it means to destroy a smart pointer or a pointer. So for a row pointer, of course, we will have to deallocate the object on the heap. I don't really consider here the constructor and the destructor, the constructor in the previous step and the constructor here. So I just consider here the heap operation. And then when we have freed up the object on the heap, then basically deallocating the pointer practically means that you fill it up with a null constant. If you look at the unique pointer, it's again the same thing. Here we have the normally inlined destructor. I'm not considering here the case when we have a custom deleter that may change the situation a bit. And then we will have to destroy the object on the heap. So basically, because the unique pointer is gone anyway, so we can decide to set the pointer to null, but it is also not necessary. The same applies to the maybe to the row pointer. Depends how precise we want to be. We have a quite complex situation again with the shared pointer, because for the shared pointer, again, we don't consider here using custom deleters. And then in that case, the destructor is inlined. And then what we have to do, we will have to decrease the strong pointer, because the shared pointer is decreased. That's why deceased. So that's why we will have to decrease the strong pointer. I put here to $1 to $2 signs. The point here is that if we are lucky, and then the counter, the strong counter is on a hot cache line, then it can be a quite cheap operation. If it is not in the cache line, it can be a bit more expensive, but it is of course not that expensive like a heap allocation. The real costly thing comes if the strong pointer reaches 0, because when it reaches 0, it means that this was the last shared pointer. So it's not enough to destroy the shared pointer, but we have to also destroy the object that points to the where the shared pointer used to point. So we have again here the cost of the destruction of the heap object, but we will have to also destroy the control block. We have to be here also a bit more precise, because if we have some other weak pointers, maybe the destruction of the control block is delayed until also the weak pointer reaches 0. So as we can see that if we have a hot cache line for the strong counter, and then we destroy a shared pointer, then it can go for it can be very cheap. But if we are for example in this situation when the two counters, the weak and the strong counter, they reach 0, then we will have a quite expensive operation. So it is not that deterministic. Now let's have a look on the copy construction. So for a row pointer, the copy construction is that I just copy over the address from one pointer into the other address, so it is very cheap. For the unique pointer, we know that this is a movable type, so there is no copy constructor, and it is not a copyable type, so it is not possible at all. Shared pointers are copyable. And then we have the usual thing here. So the copy constructor is inline, so I don't consider here any expensive operation. And then we will have to clone those two pointers, because we have seen that there are two pointers. And because we have created a new shared pointer, that's why we will have to increment the strong counter, which is again depending on the cache situation, can be more or less expensive. But we don't have here for copying a shared pointer a $3 sign. I derived from the copy constructor also the copy assignment. For the copy assignment, normally it contains two steps. So if the pointer was assigned, so it was not a null pointer, then we will have to pay the cost of the destruction, so the destruction of the previous state. at least for the unique pointer for sure. For the shared pointer, it depends if it was the last element. And then we will have to pay the cost of the copy construction. If we consider what is the cost of the move construction, then we will see here a bit different things. For the row pointer, if we want to make a decent movement, it would mean that I have to fill up the new pointer with the address, and then I have to set the old pointer to 0. So we are setting here basically 2 pointers, but this I consider to be a cheap operation, so I just gave here $1. For the unique pointer, we have again the inline move constructor, and then we have to set the new pointer that is inside the unique pointer, and then the source of the movement, there we have to set it to null. Of course, we will not do it manually. It happens from the move constructor, so that there will be less manual work compared to the row pointer. And it is also interesting that for the shared pointer, we have again the inline constructor for free, and then we will have to just clone the 2 pointers. And then the reason here is that why we don't have to touch the counters, however we do a moving, because when we do the moving, then one reference is destroyed, one reference is created. One strong reference is created, one strong reference is destroyed, and then in sum this +1 and -1 comes to 0. So it means that we don't have to touch the counters at all, and then we don't have to access that object. So basically the moving is the same cost all over the place. Move assignment cost, again, we can use here the similar formula what we have used for the copy construction. If it was assigned, of course, then we will have to destruct the object, and then we have to pay the cost of the move construction.
Wir sind hier in einem kleineren Grossraumbüro.
Bei den Leitern habe ich die Freiheit, dass ich, wenn ich anfange und wenn ich höre mit dem Arbeiten, eigentlich selber einteilen kann.
Overall, how I will do it, it's just up to me, and they give me a lot of freedom.
Für mich ist die Faszination, mit anderen Leuten einen kreativen Moment zu generieren.
Great colleagues, great environment basically.
It's really nice here, and I don't have any issues living here.
Am meisten schätze ich in den Leica Geosystems, dass wir ein sehr junges Team sind, sowie dass ich auch meine Arbeitszeit in einem gewissen Raum selber bestimmen kann.
And I could merge in my life hobby with my office job.
Das Besondere an der Leica Geosystem ist sicher die Kultur und die Dynamik, die es gibt in dem Team. Es ist jeden Tag ein bisschen anders.
We have good organization which will help you to get used to the company in the first couple of months especially.
Das ist sehr interessant und ja, macht mir Spaß.
And maybe this is the most used part, so that how expensive is dereferencing the pointer. So I mean that using the asterisk operator or the row operator. So for the row pointer, then it is an indirection. So I just put here $1. So it's normally even part of the assembler addressing scheme. In the unique pointer, the important thing is that there is no validity check. So would be possible here to maybe throw an exception or make an assertion or something like that to check the pointer, but maybe this was a design decision that they don't do it, and then they just do the normal referencing. So basically, because of that, we come to the same cost like we had for the row pointer. The same applies to the shared pointer. We also don't do here any validity check. We also dereference a null pointer. And then The interesting thing here is that in the shared pointer we have seen on the first slide about the memory consumption, that the shared pointer has 2 pointers, one pointing to the object and one pointing to this administration block. And now we can see the benefit having it inside the shared pointer and not in this control block, because we can dereference the shared pointer exactly with the same effort like we do with the unique pointer or with the row pointer. So all across the board we have the same costs. Now maybe let's wrap it up, what it means. So the cost of the smart pointers versus the row pointers. So the smart pointers are close to zero cost abstraction. We have this pay as you grow scheme. So if you have a unique pointer, then the unique pointer is more or less the same cost, or we can say this is the same cost. If you don't use custom deleters, then it is the same cost as the row pointers. And then if you need more complexity, so pay as you grow, because a shared pointer represents a more complex use case. That's why we will have to pay for that extra features, and that's why they are a bit more expensive than the normal pointers or the unique pointers. The good news here is that we quite often, especially in typed loops, we dereference these pointers, and then even if we are using a shared pointer, it has the same cost as the unique pointer when it comes to dereferencing. And now here comes this solution, the relaxing of the smart pointer, the shared pointer allocation. So as we have discussed, in the shared pointer, we have a separate control block, and this is expensive. So it is expensive. We can have a cold cache because the control block and the object on the heap, they are in two separate places, and then it can be that one is in the cache, the other one is not in the cache, so depending how far they are from each other, so it can cause some cold caches, and then we will have to do the heap allocation twice. And then if we use the stud make shared function, then we have this option that we will do only one allocation, and then in this one single allocation, we will have the control block plus the allocated object. So basically, it is improving this cold cache situation because we have a better chance that our object and the control block are close to each other, and then they will be both in the cache. And then for the heap allocation, it is also better because when we are looking for a gap inside the heap to allocate our objects, then we will have to do this only once, and then it makes it cheaper. Let's look the other. So what is the extra features what we get from the smart pointers? So one very important point of smart pointers that they express clear ownership, and then row pointers, they only contain some addresses. So if I have a row pointer and I get it back from an API, unless there is some documentation, I have no idea that if I'm supposed to delete the object what I got, or actually I just got the address of that object, and then behind the API it will be freed up. But with smart pointers, it is clearly expressed that if I receive something with a unique pointer, then as long as I keep the unique pointer on my side, the object is alive. And then the same applies to the shared pointer. So my recipe here is that I usually return from factories unique pointers, which I can later upgrade to shared pointers. And then if I want to just do some reference borrowing, so I just want to use it temporarily, then I pass the object by C++ reference. I rarely use row pointers, mostly when I go to and I use C APIs, where there is no other possibility. And the other very nice thing about smart pointers that they address a lot of shortcomings of the raw pointers, because they provide a dangling free implementation. It means that if we have memory address inside a smart pointer, then we can be sure that that is either null or it points to some valid memory. Of course, we will have to be careful here that we are not misusing it, so we don't allocate something on the heap and then we hand it into, let's say, into a unique pointer, but still we keep the address and then we delete that object, and then of course we have just tricked our new unique pointer. But if we use it correctly, then it will not happen. We also don't have a memory leak because of the RAI style memory management of the smart pointers. Makes sure that the objects are freed, and then the smart pointers also take care that at least they will not delete it twice, the same object. And then, as we have seen, this come at no extra cost. What I mean by no extra cost is that if you do a decent memory management in C++ 98, so prior to C++ 11, then you would have to also do exactly these steps what the smart pointers are automatically putting into your code. Yeah, basically this is wraps up this lighting talk. And then maybe something from my company. We are looking for good C++ developers. If you are interested, then feel free to get more information. You will find some information in the lobby room. There is a Leica table and you can get some more information. Yeah, thank you. Let me quickly have a look on the Yep. Okay. Yeah. Thank you. So if you had some questions, I will go to the Leica Geosystems table, and then I will wait for you if you have some questions, and then thank you, and then see you later. Bye bye.
If you found this video informative, make sure to subscribe our channel. Click the thumbs up if you liked it, or leave us a comment on what we could improve. If you are looking for a job in the embedded industry, or you've got one to offer, drop us a mail to jobs@embo.io. That's jobs@embo.io. And we'll make sure that you match up. My name is Stefan Bückelmann, and as long as you keep watching, we'll keep covering the internals of the embedded industry.